Welcome to this video. We will go out of order and cover one important topic which is frequently used, which is of microsimulation analysis. Microsimulation analysis in the field of traffic operations is one of the most time consuming effort. And is very detailed. So we will cover the microsimulation analysis first, and then we will resume the other chapters. So first, in 13.1 we have introduction to microsimulation modeling. To create a realistic and dependable model with reliable results, modelers are recommended to properly scope the project, which is important since microsimulation modeling requires a decent amount of time and budget. It's important to scope the project properly. If we lack appropriate budget for the microsimulation modeling, that usually yields in poor models and poor results. Choose the appropriate analysis tool, replicate the existing conditions as accurately as possible, complete the analysis, and effectively summarize and document the result. So each of the point has certain meaning to it. They are not just randomly written. They have some deeper meaning to it, which is very good point of TSAP manual. So each point is written from a point of view that these mistakes happen frequently. So this is a very good guideline, and each of them will be explained later on, and each point are important, which are frequently missed on the projects. So microsimulation models are typically complex and demand experience and careful attention. So first we need to make sure there is an experienced engineer who is doing microsimulation model, because even if there are a lot of fatal flaws in microsimulation models. And if we are not aware of fatal flaws, we may spend the entire budget and yield with poor results. So a good experienced engineer who knows latest approach and model software is needed for microsimulation models. To confirm the accurate outputs, because models are largely built on modeler defined inputs and assumptions. So we will see in one of our video that a lot of softwares, specifically the microsimulation models, allows user to input hundreds of inputs, and depending on what inputs we are putting, we can generate any realistic and unrealistic results. So let's say in real life, this is our data set. This is what real data look like. It's not for calibration. Let's say this is the real possibility of real data. Based on what parameters we are choosing, our results can lie anywhere on this system. So it's very important to have an experienced modeler, because there are a lot of inputs that can be input, and there I would call it settings instead of input. There are a lot of settings in the softwares which can be changed and which can lead us in a very, very different direction. So inputs and assumptions or settings are very important, and a lot of time in field we notice there are models with fatal flaws in it. So even though the model has been built and result has been produced, there are several fatal flaws of the models which lead us to reject the models right away. So it's very important to have an experienced engineer leading the project. In our personal opinion and personal experience, it is recommended that the modeler carefully analyze and report the results. Reporting the results is another part. We cannot just take the output and report it. There we need to know what software output is, and software output can be vast, a lot of outputs, and what they mean and which output we need. So we cannot just go and select some output. We will see that how software output needs to be carefully analyzed and figure out which output we need to report, which are compatible of industry and standards and have a capacity manual. So in addition to requiring the strong modeling judgment, model development, debugging, calibration are also resource intensive process. These processes are potentially more resource intensive than other form of analysis, and it is recommended that care be given when deciding whether microsimulation is the correct method to analyze the project. So here in this paragraph, the TSAP manual pretty much says that it's not an easy task to work with microsimulation model. So these are resource intensive processes. A good experience is needed to understand each component of the microsimulation software and each component of the processes. If we do not have good judgment, then we would likely end up with some flaws or some fatal flaws and have to redo the work. So it's important to have a complete understanding of microsimulation approach and a good time and budget in the scope. So it is recommended that these processes are potentially more resource intensive than other form of analysis. So typically microsimulation models are very time consuming, and appropriate time and budget should be allotted to microsimulation models. Purpose and intended use. So this paragraph explains the purpose of this chapter, which is this chapter explains the debugging, calibration methodology, alternative development, reporting of results. There are some limitations to this chapter. So this chapter provides the guidance provided in chapter is generalized for all microsimulation software. Further guidance on coding model features not discussed in the chapter can be found in respective user manuals. So this chapter is written from a perspective of providing a generic guideline which can be applied to all microsimulation softwares, and for detailed guideline on how to use them and how to code them within the software, how we can use that particular tools software's user manual. For example, for VSIM we can use as VSIM user manual. For CoreSim we have CoreSim user manual, and so forth. Project scope. As stated in chapter 1 of this manual, a project scoping form is typically developed to serve as the project guidance document that includes all elements discussed in the analysis methodology. This chapter outlines the scope guidance specific to microsimulation. So this chapter will help us in filling out a project scope form. So this chapter will help us with two things: figuring out project scope and fee, and actually performing the actual analysis. Study limits. So the study limits for a project are determined during the scoping process itself. The study limits incorporate the project limit plus the area of influence. Area of influence is typically the area surrounding the project which has an impact on operations in the study area. Wherever acceptable, it is recommended that model extend a minimum of one intersection or interchange both upstream and downstream uh, of the farthest intersection or interchange within the study area. So let's say this is a good picture from IIJRs. So let's say our project is from, we are working on this interchange, then we should go one interchange in this direction and one interchange in this direction. Additionally, if we are working on a project, we should go one to the nearest signalized intersection, or if there is no signalized intersection within the half mile, then we should go half mile in each direction. So that would be our study area for IIJRs, and this is also what we typically do for other projects. Not much different between IIJR and typical projects. So let's say we have a typical project like this. This is our project limit. Typically we go to one interchange down, one interchange up, assuming that there are interchanges. Otherwise we limit it to 1 to 2 miles up and down. So assuming there are interchanges within 1 to 2 miles, we will go one interchange up and one interchange in this direction, and along the cross streets we will go to the nearest signalized intersections. Section 13.6 of this chapter. For more information about incorporated unmet demand into microsimulation model. So we will look at unmet demand, which we have discussed under Q, and we will see how to address the issue of unmet demand. This is just one of the approaches, but this is a big issue, out of which one of the issues has been addressed in this manual. Then we have freeways. It is recommended that the model extend at least one interchange, including ramp terminals, beyond the study limit in both upstream and downstream direction. This additional area is included during calibration and debugging process, but the results are not always reported. So many times we do, that's another good point, is many times, let's say our project is from here to here. So for data collection, modeling and everything, we do analyze our projects one interchange up to here. However, when we are reporting the output, the TxDOT may only be interested in knowing what has happened within the project limit, or maybe a little bit here. So not everything outside of project limit is reported in the final report. However, the models and analysis and data collection, everything is built for the influence area, and majority of time the report is does include influence area, but not necessarily. Many times we run the analysis and report what is included in the project, especially if it's not an IIJR. So that discussion is here. I'll change it to blue. Arterials. Arterial model typically capture both one signalized intersection upstream and one signalized intersection downstream of the study intersections. If the signalized intersection is not present, such as in rural area, it is recommended that the network capture approximately half mile of arterial in both upstream and downstream direction. Visual inspection of field data is used to determine if more of the roadway network will be included in the analysis. So this one is, let's say we have this is our study intersection, and in half mile here, let's say we do not have a signalized intersection, but just a little bit after it, let's say 200 feet after, there is a signalized intersection. So many times we will not only go half, we will actually cover the signalized intersection. So sometimes a visual inspection of field data is used to determine if more roadways needs to be included. Like freeways, all intersection with the significant influence on the arrival pattern of the vehicle entering the network are included in the model, because there is a signalized intersection that typically impact how the vehicle arrives to this intersection. That's why we can go a little bit beyond half mile to see to capture the nearest signalized intersection. Additionally, it is recommended that all resulting congestion during peak period be captured within the study limits. If the congestion is defined on a network boundary, extend the study limit to capture the entirety of queue. If extending the study limit is no longer practical, additional information on capturing unmet demand is provided in 13.6. So this is very common. A lot of our freeway projects are in urban area. So for example, let's say this is our urban freeway, and during peak hour the congestion happens from, let's say here is downtown, then the congestion happens all the way up, then all the way to down. So let's say we are working on a project in this area. The guidance is to extend it so that we start with an area where there is no congestion. We start with time and space, both. So we start with a time interval for simulation before the onset of congestion, and end it after the congestion has been relieved. And in space, we start it where the congestion has not reached yet. However, many times the congestion occurs well outside of what we can capture. So let's say this is our project area and this is what we can capture, but let's say during 2 p.m. to 6 p.m. this thing is already filled up. So many times it's unpractical to actually move the boundary. Then what we can do is we can simulate how the vehicles are entering at the entrance point, and then we can take care of unmet demand. Unmet demand is a concept which is very important, and we have discussed this issue in chapter 2 of our video series of traffic count versus volume. Traffic count versus traffic volume, which is one of the most difficult problem in traffic field to solve. What is the difference between traffic count and traffic demand is considered one of the most difficult issues in field of traffic operations, and we have discussed this in great length in chapter 2. So one of the cause is the queue, which is stuck in the bottleneck, and that has been addressed in 13.3. However, there are other issues which are very, very difficult to address, and those has been discussed. So as an engineer, we need to know the difference between traffic count and traffic demand, and especially when there is bottleneck and queue, and having an idea on how to address them. So please refer to chapter 2 to understand more about this particular issue in a congested network. Study time periods. Study time periods are selected such that they include time prior to the buildup of congestion, like I mentioned, and end after dissipation of congestion. A simulation model is developed for a period of time that is necessary to replicate full extent of congested traffic within the study peak period and peak hour. For models that are oversaturated, the study period is typically expanded to include buildup and dissipation of congestion. Otherwise, a peak hour analysis and seeding period may be sufficient. So if there is congestion, let's say congestion is between 3 p.m. to 5 p.m., then the analysis we can go from 2 p.m. to 6 p.m. However, if there is no congestion, then we can simply use seeding time plus the peak hour time, let's say 5 p.m. to 6 p.m. One very common question that is frequently asked and frequently comes up in our field is the changing the peak hour between existing and future year. So I did not see it getting discussed here, but I'll just discuss here and maybe it's discussed somewhere else. So one very big question that comes up very frequently in our practice is peak hour, let's call it peak period in existing. So let's say we are building an existing model and the peak period is between 4:30 p.m. to 6:30 p.m. for 2 hours. Now when we grow the volume to no build and build conditions, and let's say we have built our existing model. Based on this information, we have built our existing model from, I will change the color here, so let's say we have built our model from 3:30 p.m. to 7:30 p.m. Now a very common question that comes up is in no build and build, since the volumes are much higher than existing, the congestion time goes up from 4:30 p.m. to 6:30 p.m. Let's say it went up from 4 p.m. to 6:45 or 7 p.m. Now the question is, are we going to build the model same as existing period as existing, or are we going to consider the future build congestion and we are going to build model based on what is happening in future? And based on our experience and response from one of the IIJR projects we have worked, FSWA has recommended us to extend the period for build and future scenarios. So for future, we will be actually building 3 p.m. to let's say 8 p.m. Although this is a big model. Important discussion here is the existing peak period may be different than future peak period. Future peak period most likely is longer than the existing period. So if our existing model is like this, we cannot just simply input the new volumes for future, because the onset of congestion in a future period may not be maybe much sooner than what it was in existing, and the congestion may last longer. So it's important for us to see what the congestion pattern will be for the future and appropriately adjust the model time. So this is a very common question that comes up, and I have seen report in doing both ways. So existing models are kept as it is, and I have seen some reports where the existing time has changed. So I believe this guidance and our experience tells us that whenever there is a need for future time period to be different than existing, then we should be extending the future time period models. Our future time periods should not be exactly copying existing. So existing model time periods for majority of projects is copied to future time periods, but this should not happen. We should look at future congestion patterns individually and extend the future time period as needed. So this is an important discussion to have, which we face majority of times. This question comes up in a lot of projects. Next one is MOE selections, measure of effectiveness selection. As stated in chapter 4, this manual of this manual, measure of effectiveness provide information on decision makers on performance of microsimulation model and help determine the similarity and differences between alternatives. So MOEs is to evaluate the alternatives. So some of the MOEs are, first one is control delay, which is the interesting one. We have discussed the difference between control delay and approach delay. Control delay can be calculated using time-space diagram. It can be accurately calculated using time-space diagram. However, just by building, and it cannot be calculated using microsimulation models. Microsimulation models cannot calculate control delay unless every intersections is run free in a different model, which we never do. So microsimulation model in practice, what we use cannot calculate control delay. It's a limitation of microsimulation models. However, the control delay is what is defined by highway capacity manual to define the level of service. So control delay is what defined level of service based on highway capacity manual. So a very important discussion is written here is level of service can be derived from control delay by converting all vehicle passengers equivalent to highway capacity manual methodology, which uses it can also be calculated in synchro using time-space diagram. Time-space diagram, we have looked into control delay, what does it mean, how to calculate it, we use on time-space diagram. However, microsimulation model, what it calculates is the approach delay or simulation delay, which is a delay of a vehicle when it approaches an intersection. And we will cover in one of the videos, and I believe we may have already covered on why this approach delay cannot yield. There is no way to transfer microsimulation delay into control delay. There is no one-to-one relationship. There is no theoretical or mathematical way to transfer microsimulation model into control delays, because there are three major reasons which we have discussed in other chapters. So it's very important to understand this, that the highway capacity manual level of service are based on control delay, which we cannot get it from microsimulation model. Microsimulation cannot produce this result. Otherwise, the analyst can note that level of service used is not equivalent to SCM methodology. Hence, whenever we are reporting intersection delay based on microsimulation model, intersection delay and LOS, the engineer must put a star here and put a star and say these are microsimulation delays. Microsimulation delays which are used as substitute for control delay. LOS criteria are based on control delay. So we have to put a star and say that the level of service criteria are based on control delay as per highway capacity manual. These are microsimulation delays which has been used as an proxy for control delays. So it's very important, very important to understand that what is control delay, why we can not calculate within the microsimulation model. When we are reporting, how should we exactly report it? So this discussion is provided here, which is a very good part, very good contribution from this TSAP manual. So this is something a lot of us miss, and it's a very good contribution from TSAP manual of putting a note here saying control delay control delay is what defines level of service, and microsimulation models inherently can never maybe a strong word, but cannot calculate control delay. They can only calculate microsimulation or approach approach or total delay. We have discussed about why it cannot happen theoretically in one of our chapters. Please have a look at that one. The second one, the results from the seeding period are typically excluded when reporting the control delay. Results from seeding period is excluded for everything, not only delays. So do not report seeding period. Seeding period results except the reason why seeding was done, saturation flow rate at the end of seeding time. Saturation flow rate at the end of seeding time. So at the end of seeding time, we need to see how many vehicles are entering the system, how many vehicles are exiting the system, and then that will tell us whether this seeding time is sufficient and some of the other calculations. But we should not report the results based on seeding time. So not only control delay, most of the reports are not generated. Second important one is queue. This is another tricky one compared to, so control delay is a tricky one because of how it's defined, and ideally the right way to define a level of service is the control delay. So what microsimulation gives us is a kind of a representation of a delay, but the accurate way of see how an intersection is performing is control delay. So one of the question which frequently or which can come up in our in our thinking is, why not just use approach delay within highway capacity manual to define level of service? Why we are complicating things? And the answer is the control delay is the appropriate method to actually calculate level of service. So please refer to our discussion on control delay versus actual delays or approach delays and why they differ from each other. Second one is queue. Queue is reported either average queue or 95th percentile queue. This is a tricky one. This is very, very tricky. So typically there are cases when within VSIM we can set the number of runs to 10, and there is a place where we can set the results as a different percentile, and we can set it 95th percentile. However, the results we get from the node queue results, if we have node queue results, that gives us queue and gives us average. So let's say we ran it 10 times, so run number 1, run number 2, run number 3, so on, run number 10, and then within VSIM we have average, we have standard deviation, we have minimum, we have maximum, and here we will have 95th percentile, and we have bunch of columns and one of them is queue. So the big problem with this is 95th percentile queue is not meant to calculate the 95th percentile out of the number of runs, which is what is given here. So at every run, the queue is already calculated as an average. The queue length, which is 95th percentile queue length, typically is meant to be calculated such that I will just draw it on the right hand side. The queue length is meant to be calculated such that, let's say we collect the data every 10 seconds. Then what we are trying to do is, let's say this is our roadway and we are trying to measure queue here. So in first 10 seconds the queue is 500 feet, then next is 510 feet, then next it has 520 feet, then next is 500 feet. So every 10 seconds we measure the queue, and at an intersection during one single run, then what we will have is a lot of data points, and then we calculate the 95th percentile. So 95th percentile is supposed to be calculated based on small queue observations, and this needs to be actually at least needs to be equal to cycle length. So not 10 seconds, I would say let's calculate it a multiple of cycle length. So cycle length is 120 seconds, so we can calculate it, let's say, every 200 seconds. So every 200 seconds we figure out what is the queue or the maximum queue on the approach. So every 200 seconds we are figuring out what is the maximum queue on the approach, and then we are calculating 95th percentile for each run. So this queue length is very tricky. It's not simply typically within VISIM. If we have intersection like this, we just draw a node. I'll change the color. We typically just draw a node, and the node gives us the queue length for approaches, and maybe some depending on how the lanes are drawn, it can give the queue lengths for the movement as well. So those queue lengths are average queue lengths or maximum queue lengths, and the 95th percentile queue length, which we get by setting up 95th percentile here within VISIM, is not actually the 95th percentile queue. That's where it's important to understand what software does and what we are looking for. When we are looking for 95th percentile queue, we have to put counter on each lanes. So we have to put queue counters and set them to count every certain interval, which at best we should be using a multiple of cycle length. So our cycle length, or at least exceed the cycle length, but not by much. So if our cycle length is 100 seconds, then we can use any number between 100 to 200 seconds. So what this would give us is every 100 seconds it will give us the maximum queue on the approach. Then next 100 seconds maximum queue on the approach, next 100 seconds maximum queue, and then based on those we can calculate the 95th percentile. Not us, the software can do it for us, but we need to understand which 95th percentile we are using. Just because software can give us 95th percentile does not mean it is 95th percentile. Majority of the time in reports we have seen a lot of modelers reporting the 95th percentile from the simulation run, which is completely wrong. It must be 95th percentile of the maximum queue which is getting which is at the approach. So queue length is very tricky one, and most of the time incorrectly done one, similar to control delays, which has been covered by TSAP. So another important thing to consider is queue length here. Speed. Speed includes link average link speed, and average route speed, travel time by travel time segments, total network delay, densities. So these are, I believe, straightforward. In addition to network MOEs, link MOEs are used if the results of specific roadway segments are of particular interest, especially for freeways. So link MOEs are almost always used for freeways, arterials, and not only network MOEs. Link include volume, density, speed, emission, relative delay. Add and consider a caveat when reporting density from microsimulation models, since microsimulation tools have their own way of interpreting and applying highway capacity manual. It's a very, very good guidance by TSAP is if we are reporting level of service reported in softwares, then put a star and say reported by software, reported level of service by software. Most of the time they are not compatible with HCM, even though it says they are. It's kind of good to just say, okay, this level of service is how we are getting, and the software told us this is our delay and this is the level of service reported by software, not calculated by engineer. So if we are calculating the delay and level of service by ourselves, and then we need to give the output. If level of service is given by the software, then we should properly put a star here and say, okay, this is reported by software. Level of service reported by software. Reported by software. This is very important. I cannot explain enough on how important these things are. These are small nuances that makes a model better and have our understanding better. This MOEs, and these are some other MOEs, average stop, those are not that important, we can read through it. Analysis tool selection. Due to complex and resource intensive nature of microsimulation tool, carefully consider tools based on project scope, project schedule, project type, need, complexity, and budget, which is the main one. There is often more than one suitable traffic analysis tool for a given project. Microsimulation software is often used to analyze the location with following characteristics. If the location or project is oversaturated, then there aren't many tools that can actually be used. So microsimulation is most likely to be the candidate for oversaturated conditions. Corridor with multiple hour of congestion, again we can use other tools as well, but microsimulation is typically used. Multi-lane or two-lane road where traffic signal or stop signs considerably impact capacity or operations. Note the signal warrant or stop sign warrant take priority over model results. So we have stop sign warrants, which is always stop sign warrants, and signal warrants. If those warrant suggest that a signal should be installed or not, or always stop should be installed or not, those results take priority because those are required within Texas MUTCD compared to the microsimulation results. Microsimulation are typically needed for IIJR. However, there is an ongoing debate on whether it needs to be done for rural interstate, and we will see how it plays out in future on whether TxDOT want us to use microsimulation models for rural interstate, because it's gonna drive up the cost of doing IIJR by a significant amount. Freeway widening project, access management studies, and these are several more. Data collection is a next important one.